So picking up from where we started in our last video, again, a one-way ANOVA between subjects design is a design in which we're comparing more than two groups, the means of more than two groups, and each subject's only going to be measured one time and only belongs to one of the groups. Now, when you do an one-way between subjects ANOVA, your null hypothesis is that all the means are basically the same. All the means are equal. And your alternative is at least one of the means is different than the others. 3 assumptions. The groups have to be independent. The variances should not be significantly different. And the distributions of each of the variables should be approximately normal. And if you wonder, well, what should I do if one of those assumptions isn't true? Like, what if I don't know if the distributions are normal? Or what if one of the distributions is not normal? Well, then what you would need is a technique that's beyond the scope of our class. Okay? All right. So we're going to compute a test statistic. Actually, we're not going to compute it. We're going to use technology because computing F statistic by hand is incredibly tedious. One of the most tedious things you could do without technology. Okay, but we're going to have a test statistic and p-value just like always, and we're going to find those using technology. And then we're going to calculate our degrees of freedom. And our degrees of freedom are the number of groups minus 1 in the numerator, and in the denominator, n minus k, where n is the total in all the samples and k is the number of groups. So there's going to be 2 degrees of freedom associated with this type of ANOVA. And again, when you compute the test statistic using SPSS, it'll tell you what the degrees of freedom are. So finally, an example. All right, so to test whether animal subjects consume the same amount of sweet-tasting solutions, a researcher has subjects consume one of 3 sweet-tasting solutions, either sucrose, saccharin, or polykose. The amount consumed in milliliters of each solution is shown in the table. Is there a difference in the amount of solution consumed? So what's really important to note is that the subjects are consuming only one of these. So the subject was either in the sucrose group or the saccharin group or the polykose group. These 3 numbers here come from 3 different subjects, all right? So there's 1, 2, 3, 4, 5, 6, 7, 8. There were 10 subjects that consumed sucrose, 10 different subjects consumed saccharin, 10 different subjects consumed polykose. And the question is, when I compute the average amount consumed for each of these 3 solutions, is there any difference in the means? Are the means significantly different? Okay, so we're going to use technology to find our test statistic and p-value, but let's go ahead and write our assumptions, our hypotheses. So first null hypothesis is that all the means are equal. In other words, if you want to state that more informally or in the context of the problem, there's no difference in the amount consumed of each sweetened solution. And your alternative hypothesis is that at least one mean is different. In other words, there is a difference. In the amount, etc., of consumed of each sweetened solution. Okay, so there's our first step. For our second step, our assumptions, we're going to assume that they're all fine. So we're going to assume assumptions are met. Because if they're not met, we don't have any other method to try. Okay, so in our third step, we're going to find our test statistic and our p-value. So our test statistic is 3.47. Notice we have 2 degrees of freedom, which are found based on these formulas here. So the first degree of freedom is the number of groups minus 1. So there's 3 different groups, so 3 minus 1 is 2. So that's our first degree of freedom. And for the other, it's the total number in all the samples. So if you count that up, 3 groups of 10, that's 30, minus the total number of groups, so 30 minus 3. And that's how we get the second degrees of freedom. So that's how we got these two numbers. And we have a p-value of 0.04, which we know is less than 0.05. So because we have a small p-value, we're going to reject our null hypothesis, and our conclusion is that there is a difference. In the amount consumed. In other words, one of these means is not like the other. Okay? All right, so how do we write our conclusion in APA formats? Remember, this is all our scratch work for the problem. And now what we want to do is we want to summarize it in formal language for a reader using APA format. So in general, we write our conclusion, all right? We're going to write our F and our degrees of freedom, and we're going to insert the F statistic there. The p-value compared to 0.05 or 0.01 if you got a very exceptionally small p-value. And then a summary of any post hoc test. Now we're going to cover post hoc tests in a moment, but basically our conclusion here is that one of the means is not like the other, but we would be curious which one is not like the others. Do subjects tend to consume more sucrose? Do they tend to consume more saccharin? Maybe it's polyglucose. One of these means is not like the other. Which one is different? And we're going to learn about that in a moment. That's called doing something called a post hoc test. Okay? All right, so that's the general form. So here are some examples of APA formatting for other studies. Okay? So here's one way. So notice that here it starts off with a conclusion. All right. So the 12 participants in the high dosage group had an average reaction time of 12.3 seconds. The 9 participants in the moderate group had an average reaction time of 7.4. The 8 participants in the control group had a mean of, so that tells you the data. And then here is their conclusion. The effect of dosage, therefore, was significant. So those two sentences together tell you what their conclusion was. So there's the conclusion. Here's the F statistic with the 2 degrees of freedom and the F statistic, what it was equal to. And here they give you a direct p-value. Another way of saying that, they could have also said p is less than 0.05. Here's another way of writing it, another example. A one-way analysis of variance showed the effect of noise was significant. So here's their conclusion. Okay. And then here's your F with your 2 degrees of freedom. Here's what your F statistic was, and here's the p-value. Here they could have also told you the p-value was less than 0.01. This one also went on to talk about post hoc analysis, which we're going to talk about in a moment. So this one said the effect of noise was significant. One of the means was not like the other. And then here in the post hoc analysis, it'll tell you which mean was different than the others. Okay? So for example, if we were going to start writing the conclusion of this test, what are we testing? To test whether animal subjects consume the same amount of sweet tasting saccharin. Our conclusion was a one-way ANOVA showed that animals consume different amounts of sweet tasting solutions That might be one way of writing our conclusion. Then we're going to write F and our 2 degrees of freedom. So F 2, 27 equals 3.47. And our p-value was less than 0.05. Now, we haven't talked about post-hoc analyses yet, but we will in a moment. But that's a start of how we would write our conclusion. So let's go ahead and take a look at post-hoc analysis. So post-hoc analysis, the one that's often used is called Tukey's HSD. HSD stands for honestly significant different, which means it's not like the others. And so what Tukey's HSD does is it uses pairwise comparison. In other words, it's essentially running independent t-tests using 2 groups at a time to see which of the means is not like the other. Okay? But we only are going to conduct post-hoc tests if there is a significant group, difference in the groups. So once you conduct the ANOVA, if you find that you did find significant results, like one of the means is not like the other, then we're going to do post-hoc tests. But if your result was to retain the null hypothesis, that means you don't know that one of the means is not like the other. So you will not do any post-hoc analysis because you have not found that there's a difference. Okay, so you only use post-hoc analyses to show what the difference is if you know there's a difference. Okay, so here's the post-hoc analysis. I put that data into SPSS, and this is what I found. Now, this is going to require going back to something that we studied several weeks ago, so you might be a little rusty, about confidence intervals for the difference of 2 groups. And if you look back in your notes or think back to that discussion, when you had a negative positive interval, that contains the number 0. And this is for if you take one mean minus a second mean, what are your possible answers? If 0 is a possible answer, that means that these 2 numbers could be the same. In other words, there's no difference in the groups. So whenever you see a confidence interval that has a negative number and a positive number, it contains 0. There's no difference in the groups. So what kind of intervals tell us that there's a difference between the groups? If you have 2 positive numbers, and again, this is for the answers you can get for mean 1 minus mean 2. If you know that you get a positive number, okay, you're sure you're going to get a positive number, that tells you that this number is larger than the second. Similarly, if you have a negative interval, and again, those are the answers for mean 1 minus mean 2, that tells you this one is larger. So if I look at this post-hoc analysis here, what I'm looking for are the intervals that have the same signs. So, oh, here's one. And do I see any other one? Here's one. And what are they? That's for saccharin and polykos. Saccharin and polykos. So the means of saccharin and polykos are significantly different. How did I know that? Their confidence interval had the same sign. So let's summarize the post-hoc analysis and the original ANOVA we did. So here's one way of writing our conclusion. So at first, the one-way analysis of variance showed the amount of consumed differed by type of sweetener. So this is what we had before. And here's reporting of our post-hoc analysis. Post-hoc analysis using Tukey HSD showed the amount consumed was significantly higher for polykos, and I included the descriptive statistics for polykos compared to saccharin. And here are the statistics for saccharin. And that's how you do a one-way ANOVA when you have a between subjects comparison.